The closest possible second Earth may be orbiting the star next door, or it may be a silent warning written in radiation, lost air, and red light. Proxima b circles Proxima Centauri, the nearest known star to our Sun, close enough to feel almost within reach, yet still separated from us by more than 4 years of travelling light. It sits in the habitable zone, where liquid water could exist under the right conditions, but its small, restless star may have tested that possibility from the beginning. Welcome to Boring Science Stories, where quiet science opens into deep cosmic questions. Before we begin, a gentle reminder to like, subscribe, and share the video if these calm journeys through space help you relax or think more deeply. Thank you for spending your time here. What time is it where you're watching or listening, and where in the world are you? Leave a comment below. Now, let's drift toward Proxima b and begin. Proxima Centauri does not announce itself in the sky. It is too faint for unaided human eyes, too modest beside the bright southern stars that seem to hold the attention of history, and too small to look like an obvious doorway into another planetary system. Yet it sits closer to the Sun than any other known star, a red dwarf only a little more than 4 light-years away, close enough for its name to carry an almost personal weight, and far enough that distance still turns it into a boundary. Around this star moves Proxima b, a planet whose discovery gave the nearest stellar neighbour a new kind of importance. Proxima Centauri was already a dim companion to the Alpha Centauri pair and a laboratory for the behaviour of small active stars. Afterward, it became the place where the idea of a second Earth could be placed at the shortest possible cosmic range, not as a certainty, not even as a clear image, but as a measured possibility pressed into the motion of a faint star. The closeness is the first part of the attraction, but it can also be misleading. A little more than 4 light-years sounds almost gentle when compared with the size of the Milky Way, whose stars are scattered across a disk so large that ordinary distance loses its meaning. In the language of astronomy, Proxima Centauri is near. In the language of machines and bodies, it is still profoundly remote. Light itself needs more than 4 years to cross the gap. A spacecraft moving with the fastest speeds that human engineering has yet placed into deep space would take thousands of years to make the journey. The nearest star therefore produces a strange double feeling. It is the close neighbour of the solar system, and also a place beyond every successful voyage ever attempted. That tension gives Proxima b its unusual force. Proxima b is different because it belongs to the nearest star system. Its orbit does not make it easy to know. Its surface has not been seen. Its atmosphere, if it has one, has not been confirmed in any settled way. Even so, the planet is close enough that every unanswered question feels sharper. It asks whether the first potentially temperate world beyond the Sun could be next door, or whether the closest example of an Earth-sized planet in a habitable zone might instead be a warning about how deceptive that phrase can be. The star itself shapes that uncertainty from the beginning. Proxima Centauri is not a yellow star like the Sun. It is a red dwarf, a smaller and cooler kind of star that releases far less visible light. Such stars are common in the galaxy, and that matters because they may host a vast share of all small planets. Their low brightness brings the region where liquid water could exist much closer to the star. For a planet around a red dwarf to receive a mild amount of energy, it must orbit tightly, completing its year in a short span and remaining exposed to conditions very different from those around Earth. Proxima b does exactly this. It circles close to its star, close enough that the habitable zone is not a comfortable ring resembling Earth's orbit, but a narrow region pressed inward toward a small, restless source of light. The phrase habitable zone has a quiet power, but it is one of the most easily misunderstood phrases in planetary science. It does not mean a planet is alive. It does not even mean a planet is comfortable. It only describes a range of distances where, under the right atmospheric conditions, surface temperatures might allow liquid water to persist. The right atmosphere may not exist. The surface pressure may be wrong. The planet may have lost its water early. It may have a climate divided between a scorched day side and a frozen night side. It may have chemistry that never approaches biology. Around Proxima Centauri, this caution becomes especially important. The star is small, but its behavior is not harmless. It can flare. It can send bursts of radiation into the space around it. A world orbiting close enough to be warmed by such a star is also close enough to receive its violence at intimate range. This is why Proxima b can be imagined in two opposing ways, without either image yet becoming secure. In one version, it is the nearest possible second Earth, a rocky planet with enough mass to hold itself together, perhaps enough atmosphere to move heat around its surface, perhaps enough water to matter, and perhaps a climate that has found some form of balance under red light. In another version, it is a stripped and battered world, its early atmosphere weakened by stellar activity, its surface altered by radiation, its water lost or buried or frozen in places where sunlight cannot easily rescue it. The same basic facts allow both paths to remain open because the facts are still sparse: a minimum mass, a short orbit, and a position in the habitable zone are not enough to decide the identity of a planet. They are only the first outlines of a body that may turn out to be either promising or severe. The difficulty is deepened by the nearby system itself. Proxima Centauri belongs to the wider Alpha Centauri family, linked to the brighter pair Alpha Centauri A and Alpha Centauri B across a vast but meaningful separation. The nearest stars to the Sun are not a single simple point of light, and Proxima is the faint outer member whose planet now carries the most immediate planetary question. That question also carries the history of discovery. The bright Alpha Centauri pair could be seen from southern skies, but Proxima was too dim to stand out. Its nearness was hidden by its weakness. Careful photographic comparison revealed its motion against the background stars, and later study showed its nature as a small active star. This reversal is part of its character. The nearest star was not the brightest. It was not the easiest to notice. It didn't enter knowledge by spectacle, but by measurement. In the same way, Proxima b did not arrive as an image of a blue world or a visible disk with continents and clouds. It arrived through a subtle stellar wobble, a repeated tug in the motion of the star, small enough to require patience and strong enough to change the meaning of the entire system. That mode of discovery leaves the planet partly concealed. A wobble can reveal that something is there. It can hint at mass and orbit. It can show the rhythm of a world circling a star, but it cannot by itself show oceans, deserts, ice sheets, storms, or the presence of an atmosphere. The imagination naturally tries to fill the silence with landscapes, but the evidence does not yet permit that. This is not a weakness of science. It is part of the discipline that gives the subject its shape. The nearest possible second Earth is not known because it looks like Earth. It is considered because its measured properties place it near a narrow threshold where Earth-like questions become legitimate. Proxima b is not a confirmed twin of the home planet. It is a nearby test of how much a planet can share with Earth before the differences begin to dominate. The word nearest, therefore, does more than locate Proxima b. It intensifies the uncertainty. If a promising world existed around a star hundreds of light years away, it might remain an elegant abstraction for a long time. Around Proxima Centauri, the same possibility feels more immediate, because the target sits at the edge of imaginable future reconnaissance. Telescopes may one day separate more information from the glare of the star, and ambitious probes have been proposed that could cross the distance if technologies far beyond ordinary spacecraft can be made to work. These ideas remain difficult, but they show how Proxima changes the emotional geometry of exoplanet science. It is far beyond reach, but not equally far beyond planning. For that reason, the planet becomes more than a candidate world. It becomes a question placed close enough to disturb the boundary between observation and longing. If Proxima b is temperate, protected, and geologically stable, then the nearest star may hold a planet where the basic conditions for habitability were not lost. If it is airless, irradiated, and dry, then the nearest small world in a habitable zone may show how easily the promise of red dwarf planets can fail. Both outcomes would matter. One would widen the sense of planetary possibility. The other would narrow it with equal force. Even disappointment would be informative. The star that cannot be seen with unaided eyes may still become one of the most important laboratories for understanding how common Earth-like environments truly are, and how often the galaxy offers a resemblance without refuge. The contradiction begins with the way Proxima Centauri was found. The nearest star to the Sun was not the one that commanded attention from ancient skies, and it did not reveal itself through brightness. It entered astronomy almost as a moving trace, a faint point compared across photographic plates, shifted slightly against a deeper background. That small motion mattered because nearby stars appear to drift more quickly across the sky than distant ones, not because they are racing through space in any simple way, but because their closeness makes their ordinary motion easier to measure. Robert Innes recognized this faint object near the Alpha Centauri pair as something important in the early 20th century, and the result was a quiet reversal of expectation. The nearest stellar neighbour was also one of the least visible. It had been beside the solar system all along, not hidden by distance, but by faintness. Proxima Centauri therefore became a lesson in how the universe often resists human intuition. Nearness does not guarantee brightness. Importance does not always arrive as spectacle. The same star that lies closest to Earth can disappear completely from unaided sight. Its light is weak because it is a red dwarf, a small star with only a fraction of the Sun's mass and diameter. Its surface is cooler, its visible glow dimmer, and much of its energy is released at red and infrared wavelengths, where human eyes are poorly suited to notice it. If the Sun were replaced by such a star at the centre of the solar system, the planets would be left in a colder, darker arrangement, unless they moved inward dramatically. Yet Proxima is not merely a reduced version of the Sun. Its smaller mass changes the physics inside it. A star like the Sun has a radiative interior over part of its depth, where energy can move outward through light interacting with hot plasma. Proxima is thought to be fully convective, meaning its interior is stirred more thoroughly from deep layers to surface. Hot material rises, cooler material sinks, and the star's magnetic behavior is shaped by that continual circulation. This interior motion helps build and twist magnetic fields, and those magnetic fields can store energy until they abruptly release it. The result is the second half of the contradiction. The faintest neighbour is not necessarily the gentlest one. Proxima Centauri is a flare star at unpredictable times. Magnetic energy near its surface reorganizes, and the star brightens in bursts that can send radiation outward across a wide range of wavelengths. A flare does not need the star to be large in order to be dangerous to a nearby planet. What matters is the closeness of the orbit, the energy carried by the burst, and the ability of a planet's atmosphere and magnetic environment to endure repeated impacts over long spans of time. Proxima's ordinary light is modest, but a world in its habitable zone must sit very close to receive enough warmth. That closeness turns stellar activity into planetary weather. Around the Sun, Earth is separated from the most violent solar effects by distance, atmosphere. magnetic shielding, and the relative steadiness of a middle-aged yellow star. Around Proxima, the balance is different. The habitable zone is drawn inward, and the planet that tries to live there must remain near the source of flares. This is not only a question of dramatic individual events. The deeper issue is repetition. A single burst might alter chemistry, disturb an atmosphere, or expose a surface. Many bursts across millions or billions of years could shape the entire history of a planet. Radiation can break molecules apart. Charged particles can interact with upper air. Atmospheric gases can be heated and lost more easily into space. None of these effects guarantees disaster by itself. Because planets are not passive surfaces, a dense atmosphere can shield the ground. A magnetic field might redirect some charged particles. Volcanic outgassing could replenish gases that are stripped away. Clouds, oceans, chemistry, and circulation all complicate the story. But around an active red dwarf, the question of survival becomes harder from the start. The planet is not merely receiving starlight, it is living inside the long temperament of its star. Proxima Centauri's flares also matter because they reveal the difference between average conditions and lived conditions. A planet may receive a roughly temperate amount of total energy over time, and still endure sudden episodes that change its surface environment. This distinction is central to Proxima b. A simple energy calculation can place a world in the habitable zone, but biology and climate would have to cope with extremes, not averages alone. On Earth, solar storms can disturb radio systems, satellites, and auroras. Even though Earth is far from the Sun compared with Proxima b's distance from Proxima Centauri, around the red dwarf, a flare arriving from much closer range would matter more intensely, especially if the planet lacks a strong protective envelope. The faint star therefore becomes a source of both invitation and warning. Its low luminosity makes small planets easier to detect through the tug they exert, and its habitable zone produces short orbital periods that can be measured repeatedly. This is one reason red dwarfs are valuable targets in exoplanet research. Their small size makes the signals of planets stronger in relative terms. Their abundance means they may host a large fraction of all rocky worlds in the galaxy. Yet the same features that help discovery also create difficulty for habitability. A planet close enough to be warmed may be close enough to be locked by tides, battered by radiation, and exposed to a long youth in which the star may have been brighter and more active than it is now. Proxima's smallness is therefore not simple mercy. It is part of a system where the conditions that make planets detectable and common may also make them vulnerable. The star's long future adds another layer to the paradox. Red dwarfs burn their fuel slowly, because their interiors can mix material efficiently. They can use a larger share of their hydrogen than stars like the Sun. Proxima Centauri may remain on the main sequence for timescales far beyond the future lifetime of the solar system. In one sense, that sounds like stability almost beyond imagination. A small red star can shine for trillions of years, carrying its planets through eras after larger stars have changed, swollen, or faded. But longevity does not mean kindness. A star can live for an immense duration, while subjecting nearby planets to harsh early conditions and repeated energetic events. Time alone does not make a world habitable. It only gives processes more room to work, whether those processes build stability or remove it. For Proxima b, the star's future cannot be separated from its past. If the planet lost too much atmosphere or water during the star's active youth, then later quietness would arrive after the damage was done. If it retained or rebuilt an atmosphere, the same long stellar lifetime could become a gift, allowing climate and chemistry to continue under steady red light for spans that dwarf Earth's remaining habitability. The contradiction is not resolved by calling Proxima hostile or gentle. It is both less luminous than the Sun and able to produce radiation hazards that matter precisely because its planets must orbit close. It is small enough to be visually unimpressive and active enough to dominate the fate of worlds around it. It is ancient in its patience and sudden in its surface violence. Even its place in the Alpha Centauri system reinforces the theme. Proxima is gravitationally associated with two brighter stars that outshine it completely in human perception. Yet the most discussed planet in the system orbits the dim outer member. The star that looked least promising to casual sight has become the one carrying the most immediate question of habitability. That is why the study of Proxima Centauri cannot remain only a study of a star. It becomes the first condition in the story of Proxima b. Before the planet can be imagined as oceanic, dry, frozen, or alive, its parent star has to be understood as the force that writes the rules. Its faintness places the habitable zone close. Its magnetism fills that closeness with risk. Its long life offers time. Its flares threaten what time might protect. The nearest stellar neighbour is not a calm lamp waiting beside the solar system. It is a small, persistent engine whose quiet red glow carries sudden releases of power. And any planet that circles near enough to be warmed must also circle near enough to be tested. The pale red dot campaign began with a star that had already become familiar and still refused to become simple. Proxima Centauri had been watched for years, measured in brightness, motion, flare activity, and spectral lines. Yet the question of planets around it remained difficult because the very behaviour that made the star interesting also made it noisy. A small active star does not sit quietly while its planets tug on it. Its surface shifts. Magnetic regions rotate into view and out of view. Flares disturb the light. Spots and bright patches can imitate or obscure signals that would otherwise look planetary. The search for Proxima b therefore did not begin with a picture of a world, or with a clean announcement from a calm star. It began with a difficult separation between motions caused by orbiting mass and variations caused by the star itself. That distinction mattered because the expected planet, if it existed, would not pull strongly. It would be small, close, and hidden, leaving only a slight rhythm in the star's radial velocity. The motion of the star toward and away from Earth, measured through tiny shifts in its light. Radial velocity is one of the quietest forms of detection in astronomy. It depends on the fact that a planet does not truly orbit a fixed star. Both planet and star orbit their common centre of mass, though the star's motion is usually far smaller. When the star moves slightly toward Earth, its spectral lines shift one way. When it moves slightly away, they shift the other. The change can be extremely small, but repeated measurements can reveal a pattern, and a pattern can imply an unseen companion. In the case of Proxima Centauri, the desired signal was almost modest enough to disappear inside stellar behaviour. The possible planet would not make the star visibly swing across the sky. It would only impress a slight, repeating velocity change on a red dwarf already full of magnetic restlessness. The pale red dot effort was built around this problem. It used careful observations over many nights, supported by earlier data, to test whether the suspected rhythm could survive the star's own variability. The name carried a deliberate echo of Earth's pale blue dot. But the object being pursued was not blue in any known sense. It was a possible world under red light, orbiting the faintest member of the nearest stellar system. The campaign had to ask a narrow question with unusually large consequences. Was there a periodic signal in Proxima's motion that repeated with the stability expected from a planet, rather than the irregularity of stellar activity? The answer that emerged was cautious, but it was strong enough to change the system. A signal appeared with a period of a little over 11 Earth days. It was consistent with a planet at least roughly Earth mass. orbiting close to Proxima Centauri, receiving enough energy to fall within the broad region called the habitable zone. That result became Proxima b. The discovery was powerful not because it revealed a landscape, but because it placed a rocky planet candidate at the nearest possible stellar address. The signal itself was small, yet the implication was enormous. The closest star to the Sun did not appear to be alone. It had at least one small planet in the region where temperature, atmosphere, and pressure might, under the right circumstances, allow liquid water on a surface. This was not the same as finding life. It was not even the same as finding water. But it transformed Proxima Centauri from a difficult red dwarf into a system with a specific planetary question. Before the discovery, Proxima was a nearby star with theoretical importance. Afterward, it became a place. The measurement of Proxima b also showed why exoplanet science often advances by inference before image. No telescope resolved the planet as a disk. No instrument saw continents, clouds, ice, or oceans. The evidence came from the star's motion, from the repeating displacement of spectral lines, and from the ability to rule out competing explanations well enough for a planetary interpretation to hold. That method carries both strength and limitation. It can find worlds that are otherwise invisible, especially around small stars where the tug of a low-mass planet is easier to detect. It can reveal orbital periods and minimum masses. It can place planets into rough thermal categories, but it cannot complete the story. A radial velocity signal says that something pulls on the star with a certain rhythm. It does not say whether that world has air. It does not say whether its surface is wet or dry. It does not say whether its minerals record a violent youth or a long climate equilibrium. Proxima b entered knowledge as a gravitational fact before it could become an environmental one. That order is important. It keeps the discovery from being either too small or too grand. Too small. And the planet becomes only a line in a catalogue. Too grand. And the phrase nearest Earth-like world begins to outrun the evidence. The better interpretation lies between these extremes. Proxima b is a planet candidate whose mass and orbit make Earth-like questions reasonable, while almost every Earth-like answer remains unresolved. Even the mass is a lower limit from the radial velocity method, because the true mass depends partly on the tilt of the planet's orbit relative to the line of sight. If the orbit is seen nearly edge-on, the measured minimum mass comes close to the real value. If the tilt is different, the planet may be more massive. This does not erase its significance, but it widens the uncertainty around its nature. A world only somewhat more massive than Earth could remain rocky. A larger one might begin to resemble a different class of planet, depending on composition and formation history. The signal gives a foothold, not a complete identity. The orbit gives another clue. Proxima b circles its star quickly because the habitable zone around a red dwarf lies close in. A year there lasts only days by Earth's calendar, and this closeness makes the planet easier to confirm because repeated orbits produce repeated signals in a manageable observing period. Yet the same closeness folds danger into the discovery. A planet near enough to tug the star in a short rhythm is also near enough to be shaped by tides and stellar activity. The finding, therefore, carried its own tension from the beginning. The very properties that made Proxima b detectable and potentially temperate also placed it in the region where the star's flares, radiation, and gravitational locking could become decisive. The discovery did not settle whether the planet was a refuge or a ruin. It only moved the question from speculation into measured reality. That shift changed the meaning of the Alpha Centauri neighborhood for generations. The nearest stars had served as symbols of interstellar distance, bright points and faint companions that mark the first step beyond the Sun. Proxima b turned that first step into a planetary target. The nearest possible destination was no longer only a star. but a world whose conditions could be tested in future by better instruments. Even the absence of direct images became part of the pull. The planet was known enough to name and model, but not enough to picture with confidence. It was close enough to invite missions in principle, but far enough to remain beyond anything already accomplished. This is why the discovery of Proxima b felt larger than the modest data that supported it. Science often changes not by providing a complete scene, but by forcing a new question to become unavoidable. The Pale Red Dot campaign did exactly that. It took a faint, active, nearby star and extracted from its shifting light the rhythm of a planet. From that rhythm came the possibility that the nearest star hosts a small world in the right thermal neighborhood for water. And from that possibility came a more difficult demand. The next task was no longer to ask whether such a planet might exist. It was to ask what kind of world could endure so close to Proxima Centauri, and whether the meaning of the habitable zone survives contact with the star that defines it. Proxima b sits inside a phrase that sounds calmer than the planet may be. The habitable zone gives an orbit a promise, because it marks the distance from a star where liquid water might survive on a rocky surface under the right atmospheric conditions. Around Proxima Centauri, that zone lies close to the star, compressed inward by the dim red light of a small stellar body. A planet there does not receive warmth in the same geometry as Earth. It circles quickly, under a sky that would be dominated by a cool red sun, and every estimate of temperature begins with assumptions that are still unverified. The habitable zone is therefore not a verdict, it is a first filter. It says that the energy arriving at the planet is not obviously too much or too little for water in principle. It does not say that water is present. It does not say that the surface pressure is suitable. It does not say that clouds, gases, ice, rock, and stellar activity have settled into anything stable enough for life. This distinction is where Proxima b becomes most interesting and precarious, because the phrase nearest potentially habitable planet can sound almost like a discovery of a place, when it is really the discovery of a condition that may or may not have survived. On Earth, the meaning of habitability depends on linked protections. The distance from the sun matters, but so do the atmosphere, the oceans, the carbon cycle, the magnetic environment, the rotation of the planet, the chemistry of the crust, the timing of impacts, and the moderation of solar energy. Earth is not habitable because it occupies a mathematical ring alone. It is habitable because many systems have remained within workable limits for a long time. The habitable zone isolates one part of that larger arrangement. It is useful because starlight is often the first thing that can be estimated for a distant world, but it is incomplete for the same reason. It begins from what can be measured early, not from everything that matters finally. Proxima b exposes that incompleteness with unusual force. Its orbit suggests a possible surface temperature range, but the star it circles raises questions that cannot be absorbed by temperature alone. A mild average flow of light does not erase flares. A favourable distance does not guarantee an atmosphere. A rocky size does not promise oceans. The word Earth-like becomes fragile when the only confirmed similarity may be scale and a thermal neighbourhood. There are several ways a planet can occupy the habitable zone and still fail to be habitable. It may have formed with too little water, leaving a dry surface where warmth only bakes minerals. It may have formed with too much volatile material, producing a deep ocean world unlike Earth's exposed continents and shallow seas. It may have lost its atmosphere early, leaving no stable pressure for liquid water. It may have kept a dense atmosphere rich in greenhouse gases and become too hot. It may have become locked in an ice state, or it may be tidally locked in a way that divides climate into harsh extremes, with one hemisphere receiving constant light and the other remaining in permanent darkness. None of these outcomes contradicts a habitable zone orbit. They show why the orbit alone is not enough. For Proxima b, even the simplest measure of warmth depends on what the air is doing, and the air is exactly what remains uncertain. A planet without an atmosphere can have a theoretical equilibrium temperature, but that number is not the lived climate of a world. It is a stripped calculation, a starting point that ignores winds, clouds, pressure, humidity, greenhouse trapping, and heat transport. Add an atmosphere, and the same starlight can produce a very different surface. A thin atmosphere may offer little protection and poor heat movement. A thicker one may carry warmth from the day side to the night side. Clouds could cool the day side by reflecting light, or they could trap infrared heat. Depending on their height and composition, carbon dioxide could prevent freezing, or in excess could drive overheating. Water vapor could support a climate, or amplify warming. The same orbital placement can lead to multiple planetary futures because climate is not a single dial. It is a network of feedbacks, and many of Proxima b's feedbacks are hidden. The uncertainty does not make the habitable zone meaningless. It makes it provisional. It gives Proxima b scientific priority because worlds outside that range are less likely to permit surface liquid water under ordinary assumptions. A planet too close to its star may be pushed into runaway greenhouse conditions, where water vapor builds in the atmosphere, absorbs heat, and helps the planet lose its oceans. A planet too far out may freeze unless a strong greenhouse effect compensates. The habitable zone is a way of narrowing the search, not of closing the argument. Around stars like Proxima Centauri, the narrowing is especially valuable because small planets can be common, yet the zone where water might persist is so close that additional hazards gather around it. Habitability becomes a balance between enough energy and too much exposure. The planet must be near enough to thaw, but not so vulnerable that the same nearness destroys the atmosphere needed for liquid water to matter. This balance may have shifted over time. Red dwarfs can spend long early periods in a brighter and more active state before settling into their mature dimness. If Proxima b has always orbited near its present distance, it may once have received much stronger energy while its star was young. That early phase could have driven water loss before the planet ever entered the calmer conditions suggested by its current orbit. Ultraviolet radiation can break water molecules apart in an upper atmosphere, allowing hydrogen to escape more easily into space, over long spans. This process can drain a planet's water inventory, especially if the atmosphere is exposed and the star remains active. A world now sitting in the habitable zone may therefore be a survivor of an earlier trial, and the severity of that trial depends on formation history, initial water supply, atmospheric mass, magnetic shielding, and stellar evolution. Present location is only a snapshot. Habitability is a biography. This is one reason Proxima b resists a clean label. Calling it a second Earth places too much weight on a resemblance that has not been demonstrated. Calling it a disaster also risks moving too quickly, because planets can preserve or regain conditions in ways that models do not fully settle. A thick atmosphere might redistribute heat. A deep ocean might survive beneath ice. Volcanism could release gases after earlier losses. A magnetic field could help reduce atmospheric erosion, though it would not make the planet immune to radiation. Even a harsh surface would not fully rule out protected environments beneath rock or ice, though such possibilities move away from open seas under a breathable sky. The proper meaning of the habitable zone is not comfort, it is conditional access to a question. Proxima b has that access. The nearest candidate naturally invites stronger language, because proximity makes it feel less abstract than distant worlds found around faint stars and crowded survey fields. Yet nearness does not improve the planet's climate. It improves the chance that future observations may clarify it. That is the discipline the system demands. The planet is close enough to become a serious target, not close enough to become familiar. Its position in the habitable zone makes the next questions worth asking, not already answered. The strongest statement is therefore more restrained and more enduring than the headline version. Proxima b is a nearby rocky world candidate receiving a level of stellar energy that could, under the right circumstances, permit surface liquid water. Every important phrase in that description carries a condition. Nearby does not mean reachable with present spacecraft. Rocky remains tied to mass and composition assumptions. Receiving energy does not define climate. Surface liquid water depends on air, pressure, temperature, and history. Under the right circumstances is not a minor qualification. It is the centre of the matter. The habitable zone places Proxima b at the threshold, and thresholds are not destinations. They are places where different futures remain possible until evidence forces them apart. In that sense, the most important thing about Proxima b may not be that it resembles Earth, but that it reveals how carefully Earth-likeness has to be earned. A planet can sit in the right orbit and still lack the deeper architecture of habitability. It can receive enough warmth and still lose the substances that make warmth useful. It can be close enough to study and still distant enough to deny its surface. The phrase habitable zone opens the door only slightly. Beyond it, Proxima b remains suspended between promise and warning, a world whose orbit invites hope while every missing detail holds that hope in careful restraint. Proxima b receives its warmth from a star that can change character. In ordinary light, Proxima Centauri is dim and small, a red dwarf whose habitable zone is pulled inward close to the stellar surface. But the quiet appearance of the star is not the same as quiet behaviour. Its magnetic field can twist, store energy, and release that energy suddenly in flares, sending bright bursts of radiation outward into the system. For a planet as close as Proxima b, these events are not distant weather. They are part of the environment. The planet does not merely orbit within a comfortable band of average starlight. It circles inside a region where ultraviolet light, X-rays, charged particles, and magnetic disturbance may arrive again and again, each event brief by human measure but cumulative across planetary time. This is where the first simple image of a second Earth begins to lose its softness. The problem is not that Proxima Centauri is bright like the Sun. It is that a low-luminosity star can still be violent in the wavelengths that matter most to an atmosphere. Visible light warms a surface. Higher energy radiation can alter the upper air, break molecules apart, and help open escape routes into space. The closer a planet orbits, the more concentrated these effects become. Proxima b sits close because it must. If it were placed at Earth's distance from a star this faint, it would be far too cold for surface water. Its possible temperance is purchased by proximity, and every flare has a shorter distance to cross before it reaches the planet. Around such a star, the distinction between sunlight and space weather becomes less comfortable. A flare begins in magnetic stress. Stellar plasma is threaded by magnetic fields, and in active regions those fields can become tangled and strained. When they reconnect into a lower energy arrangement, they release stored power as radiation and particle acceleration on the Sun. This process can produce solar flares and coronal mass ejections, and Earth feels the results mainly through changes in the upper atmosphere, geomagnetic storms, and auroras. Around Proxima Centauri, the basic physics is related, but the planetary geometry is more severe. Proxima b is far nearer to its star than Earth is to the Sun, so an outburst of comparable or even smaller total energy can still be more consequential at the planet. The danger is not only brightness, it is the combination of closeness, repetition, and atmospheric vulnerability. A planet can survive harsh events if it has enough shielding and recovery. The question is whether Proxima b was given those protections and whether they endured. Ultraviolet radiation matters because it can drive photochemistry, the chemistry caused by light. Some photochemistry is useful for atmosphere and climate. On Earth, ultraviolet light helps shape ozone chemistry, while the ozone layer itself filters much of the harshest radiation from the surface. But too much high-energy radiation can become destructive. It can split water vapor into hydrogen and oxygen in the upper atmosphere. Hydrogen, being light, can escape more easily. Over long periods, this is one pathway by which a planet can lose water. If Proxima b once had oceans or abundant vapor during the star's active youth, repeated ultraviolet exposure could have helped erode that inventory, especially if the atmosphere was heated and expanded at the same time. What remains afterward might not resemble the surface that existed at the beginning. A world can pass through the habitable zone after the ingredients of habitability have already been diminished. X-rays add a different form of pressure. They deposit energy high in the atmosphere, heating gases and changing the balance between bound air and escaping air. When upper layers are heated, they can expand outward, making it easier for particles to be stripped away by stellar wind or lost through thermal escape. Charged particles from the star can then interact with this swollen upper atmosphere, dragging ions away along magnetic pathways or enhancing chemical loss. A magnetic field around the planet could help redirect some charged particles, but it would not simply cancel the problem. A strong magnetic field can protect parts of the atmosphere, yet it can also guide particles toward polar regions. Its effect depends on field strength, stellar wind pressure, atmospheric composition, and the planet's rotation and interior. Without knowing these properties, Proxima b remains a case study in conditional survival rather than a clearly protected world. The early history of Proxima Centauri may be especially important. Red dwarfs can remain active for long periods, and their young stages may expose close planets to intense radiation, while the planets are still forming atmospheres and cooling from violent beginnings. If Proxima b formed near its present orbit, it would have spent its earliest eras in a zone of strong stellar influence. It may have endured greater luminosity, stronger activity, and more frequent outbursts before the star settled into its later state. The result could be a planet whose present energy balance looks promising only after the most damaging phase has passed. This is one of the central traps in interpreting nearby red dwarf worlds. A planet observed today may seem to receive the right amount of light, but habitability depends on what happened before the present became calm enough to measure. The atmosphere that would make the present orbit meaningful may have been tested during a much harsher past. Still, radiation does not lead automatically to a dead surface. It creates constraints. A massive atmosphere rich in carbon dioxide or nitrogen could absorb much of the incoming high-energy radiation before it reached the ground. Oceans, if they survived, would provide a powerful shield for chemistry beneath the surface. Rock itself can protect subsurface environments from radiation. Even on a planet exposed to severe flares, protected niches could exist below soil, ice, or water. The difficulty is that these possibilities move the image away from an open Earth-like world. They suggest that if Proxima b is habitable at all, its habitability may be partial, buried, or dependent on atmospheric conditions unlike those of Earth. The planet may be less a mirror of the home world than a narrow experiment in endurance. That distinction matters because life, if it ever emerged there, would not only need liquid water and useful chemistry, it would need persistence through disturbance. Flares could repeatedly alter surface radiation levels. Atmospheric chemistry could swing after major events. Ozone-like shielding, if it existed, might be damaged and rebuilt. Climate could be affected indirectly if the star's activity changed the composition or escape rate of key gases. For simple organisms under rock or water, some of these changes might be survivable. For a complex biosphere exposed on land, they might be severe. It is not necessary to imagine a planet constantly sterilized by every flare. The quieter possibility is that the surface may never remain benign for long enough, or over wide enough regions, for Earth-style complexity to become likely. Habitability is not a switch. It can be uneven, intermittent, and hidden. There is also a paradox in radiation itself. The same energetic light that threatens atmospheres can power chemical reactions. On early Earth, ultraviolet light may have helped drive some prebiotic chemistry, even as too much of it would have been destructive. A completely shielded world might lack certain useful energy sources, while an overexposed one might lose fragile molecules faster than they can assemble. Proxima b may sit somewhere inside this tension. Its star could provide bursts of energy that create chemical opportunities, but those bursts may come with atmospheric erosion and surface hazard. The line between stimulation and destruction depends on details that are still unknown: the thickness of the air, the presence of water, the chemistry of the surface, the frequency of major flares, and the planet's ability to recover after each disturbance. Without those details, radiation weather remains neither a sentence nor a reprieve. It is a pressure that must be built into every plausible version of the planet. This pressure changes the way Proxima b should be imagined. The strongest picture is not a calm blue sphere waiting beside the nearest star. It is a world under repeated testing, where each layer of protection has to justify itself. Atmosphere, magnetism, ocean, ice, rock, and chemistry all become shields of different kinds, and none can be assumed. If those shields are present and strong, Proxima b may still hold environments where water and stability persist. If they are absent or weakened, the habitable zone may only mark the place where the planet once had a chance. The radiation does not erase the mystery. It sharpens the requirement for evidence. Until the atmosphere is detected, until its composition is constrained, until the flare history is better understood, the planet remains suspended between two readings of the same closeness, the closeness that warms it, and the closeness that may have stripped away what warmth was meant to sustain. Proxima b's atmosphere is the missing layer that would decide whether the planet's promising orbit has any practical meaning. A rocky world can sit at the right distance from its star and still be nothing more than exposed stone if the gases above it have been stripped away, frozen out, or never supplied in the first place. Around Earth, the atmosphere is so familiar that it can seem like background, but for habitability it is closer to an operating system. It sets pressure at the surface, shapes temperature, carries water through clouds and rain, filters dangerous radiation, and moves heat between regions that would otherwise drift toward extremes. Without it, liquid water becomes difficult to maintain openly for long periods. With the wrong kind of it, a planet can become either too cold, too hot, too chemically hostile, or too thinly protected. Proxima b cannot be understood as a second Earth until this invisible envelope is brought into the center of the question. The planet's nearness to Proxima Centauri makes that question unusually severe, because any atmosphere there would have to endure not only ordinary escape into space, but the long pressure of stellar activity from a close red dwarf. Atmospheric loss begins with simple vulnerability. Gas molecules at the top of an atmosphere are held by gravity, but they are not locked in place. Heat, radiation, collisions, and charged particles can push some of them onto paths that escape the planet altogether. Light elements are most easily lost, and hydrogen is especially fragile once it reaches the upper air. If water vapor climbs high enough and ultraviolet radiation splits it apart, hydrogen can leak away over time, leaving the planet drier than before. More energetic processes can remove heavier gases as well, especially when the upper atmosphere is heated and expanded. Stellar wind can strip ions from the outer layers. Flares can change chemistry and increase escape rates. Impacts can blow off portions of air, while volcanism and interior outgassing can add gases back. The atmosphere is not a fixed possession. It is a balance between sources and losses, and on Proxima b that balance may have been tested from the beginning. The earliest era may matter more than the present. Young red dwarfs can spend extended periods shining with more intense high-energy radiation relative to their later calm, and a close planet in the habitable zone of an older red dwarf may once have been exposed to conditions that were far less forgiving. If Proxima b had a young ocean, or a steam-rich atmosphere, the star's early activity could have pushed water into the upper atmosphere, broken it apart, and allowed hydrogen to escape. Oxygen might then remain behind for a time, but that would not automatically mean biology. Abiotic oxygen, produced without life, can build up under some loss scenarios, especially if there are not enough surface reactions to absorb it quickly. Even a gas that sounds familiar from Earth can carry a different meaning on another world. An atmosphere rich in oxygen around Proxima b would not be a simple signature of life unless it were understood with water loss, stellar radiation, surface chemistry, and other gases. The atmosphere, if found, would still have to be interpreted like evidence from a long and uncertain crime scene. Keeping air is only one part of the trial. The atmosphere must also be the right kind of air. A very thin atmosphere might allow surface temperatures to swing drastically, especially on a tidally influenced planet with nearly fixed patterns of illumination. A very dense atmosphere could spread heat efficiently, but it might also create crushing pressure or a powerful greenhouse effect. Carbon dioxide could warm a cold world, yet too much could alter the climate beyond Earth-like conditions. Nitrogen would be useful as a background gas, but difficult to detect directly from afar. Water vapor would be central to habitability, but it could also reveal ongoing loss if found high in the atmosphere. No single gas would settle the issue on its own. The composition, structure, pressure, and history of the atmosphere would have to be read together. Around Proxima b, this interpretation would be harder because flares can alter atmospheric chemistry and perhaps mimic or erase signals over time. Climate depends on circulation as much as composition. If Proxima b is tidally locked, an atmosphere would become the main bridge between light and darkness. On the day side, starlight would warm the ground or ocean. On the night side, heat would radiate away into space unless air or water carried energy across the planet. With too little atmosphere, gases could freeze out on the dark side, thinning the air further and weakening the climate. With enough atmosphere, winds could move warmth around the globe, softening the divide and perhaps allowing stable regions near the terminator. The boundary between day and night. Clouds could gather on the illuminated hemisphere and reflect some incoming light, reducing overheating. The planet's fate may therefore depend on a threshold that cannot yet be seen. Below it, the world may separate into extremes. Above it, circulation may knit those extremes into something more durable. The atmosphere would also determine how the surface receives the star's radiation. A dense protective layer could absorb high-energy radiation before it reached the ground, while a thin or absent one would leave the surface exposed. On Earth, the atmosphere does not simply provide breathable air. It is part of the planet's radiation shield, with ozone and other molecules filtering high-energy light. Proxima b may not have Earth-specific chemistry, and it may not have ozone in the same way, but any viable surface environment would need equivalent protection. Life beneath water, ice, or rock could avoid much of the radiation danger. But that again changes the nature of the planet's possible habitability. It would not be the open surface Earth that the phrase second Earth often suggests. It would be a world where survival depends on depth, cover, and the endurance of hidden reservoirs. The difficulty is that atmospheres can be both protective and fragile. The same envelope that shields the surface presents an outer edge to the star, and that edge can be worn down. A planet close to an active red dwarf may need a thick atmosphere to protect its surface, yet a thick atmosphere gives the star more material to heat, ionize, and erode. A magnetic field might help, but Proxima B's rotation may be slow if it is tidally locked, and the connection between rotation, interior motion, and magnetic strength is not simple enough to assume either failure or protection. Some tidally locked planets could still maintain magnetic fields if their interiors remain active. Some faster rotating worlds might still be weakly shielded. The deeper question is the planet's interior energy, composition, and cooling history, all of which are hidden. Volcanism could replenish gases lost to space, but only if the interior contains the right volatiles and remains active enough to release them. Plate tectonics, if present, could help regulate carbon dioxide over time, but there is no evidence yet that Proxima b has such a cycle. The trial of the atmosphere therefore reaches beneath the surface into the structure of the planet itself. Future telescopes may eventually search for atmospheric signatures, but Proxima b is a difficult target because it does not appear to transit its star from Earth's point of view. Astronomers cannot easily use the most direct method of watching starlight pass through its atmosphere. Instead, they may need direct imaging or other techniques capable of separating the faint planetary signal from the star's glare. The planet's tight orbit keeps it close to the star in the sky, while stellar flares and spots add noise. Any detected signal would have to be disentangled from the behavior of Proxima Centauri itself. The atmosphere may be the most important evidence, but it is also among the hardest to obtain. Until that evidence arrives, Proxima b remains balanced between models. Some models allow a surviving atmosphere, especially if the planet began with enough volatiles, formed farther out, migrated inward, or developed a strong protective and replenishing system. Other models suggest severe loss, especially under early stellar activity and close orbital exposure. Both sides can be scientifically reasonable because the missing information is decisive. The planet's mass, orbit, and stellar environment define the courtroom, but the atmosphere is the witness that has not yet appeared. If it is substantial, stable, and chemically compatible with long-lasting surface water, Proxima b becomes one of the most important worlds in the search for habitability. If it is gone, thin, or chemically marked by catastrophic loss, the planet becomes important in a different way, as evidence that the habitable zones of active red dwarfs can offer warmth without refuge. The same invisible layer would decide whether Proxima b is protected enough for possibility, or exposed enough that the promise of its orbit has already been spent. Proxima b's orbit is close enough that gravity may have taken hold of its rotation. Over long spans, tides raised by Proxima Centauri can slow a planet's spin until the same hemisphere faces the star again and again, a state called tidal locking. The Moon shows the familiar version of this relationship with Earth, always keeping one face turned toward the planet, but around a red dwarf the consequence can be planetary climate rather than a silent lunar face. Proxima b may not have days and nights that pass in a familiar rhythm. It may have one side held in persistent red daylight and another turned permanently away, with a ring of transition between them where the star rests low near the horizon. This possibility does not make the planet uninhabitable by itself, but it changes the question completely. Earth's rotation spreads sunlight across its surface in a moving pattern. Proxima b may have to solve habitability under fixed illumination, where geography and climate are arranged not around seasons as they are known on Earth, but around the permanent direction of the star. The first image that comes from tidal locking is often too simple, one hemisphere scorched, the other frozen, and only a narrow twilight strip between them. That image is useful as a warning, but not as a complete model. a planet with little or no atmosphere could indeed divide sharply. The dayside rock would absorb light and radiate heat back into space, while the night side would cool without rescue. Any gases present might migrate toward the dark hemisphere and freeze there, further thinning the air and making the contrast worse. Water, if exposed, could evaporate from the warm side or accumulate as ice on the cold side. In that bare version, tidal locking is harsh because there is no medium strong enough to move energy across the planet. The star does not have to burn the day side into disaster for the system to fail. It only has to let the night side become a trap where warmth and volatiles are lost into darkness. With an atmosphere, the story can change. Air heated on the day side would rise, flow outward, cool, sink, and return, building circulation that might carry energy across the terminator into the night side. The stronger and denser the atmosphere, within limits, the more effectively it could soften the contrast. Winds might become one of the central engines of habitability, instead of ordinary day and night. Proxima b could have a global pattern shaped by a permanent hotspot under the star. High altitude flows away from that region, and returning winds along lower layers. Clouds might form where warm air rises, especially on the illuminated side, reflecting some starlight back into space and cooling the surface below. This cloud feedback has been proposed for some slowly rotating or tidally locked planets, and it shows why a fixed dayside is not automatically a furnace. The same geometry that concentrates light can also concentrate cloud cover, creating a reflective shield above the most intensely warmed region. Yet the protection depends on water, air, pressure, and circulation that have not been observed. The dayside of Proxima b, if moderated by clouds and atmosphere, could be less hostile than it first seems. Its red dwarf light would arrive with more energy and longer wavelengths than sunlight from the sun, affecting how ice, water vapor, and clouds absorb and reflect radiation. The colour of the star is not only an aesthetic detail, it enters the physics of climate. Ice and snow reflect visible sunlight efficiently on Earth, helping cold regions stay cool. But under redder and infrared rich light, their reflective behaviour can differ. Atmospheric gases also absorb some wavelengths more strongly than others. A climate model for Proxima b cannot simply move Earth inward and tint the sky red. It has to rebuild the exchange of energy between star, air, ocean, ice, and rock under a different spectrum. Even the habitability of the terminator, the boundary region between permanent day and permanent night, depends on this exchange. The twilight zone may sound like the natural refuge, but it would not necessarily be calm. It could be a belt of strong winds, steep temperature gradients, and complex cloud behaviour. If water exists there, it may gather in seas, glaciers, or cycles of sublimation and condensation unlike Earth's weather. The star would not rise or set. The climate would be geographical, with position relative to the fixed star replacing the familiar clock of daylight. A stable terminator environment could be possible, but it would be stability of a very specific kind, dependent on atmospheric mass and heat transport. Too much contrast could freeze volatiles out. Too much greenhouse warming could push the dayside beyond comfort. Between those extremes lies a narrow range of possibilities that remains open only because the atmosphere remains unknown. Oceans, if present, would add another transport system. Water stores heat better than rock and can carry it through currents. If the ocean is connected, on a tidally locked Proxima b, an ocean could help move warmth away from the day side and reduce the risk of extreme freezing on the night side. If the planet were covered by a deep global ocean, its climate might be less dependent on continents and more controlled by circulation between the heated hemisphere and the dark hemisphere. But that scenario raises its own problems. A water world without exposed land may struggle with some long-term chemical cycles important to Earth's climate. A shallow ocean might be more vulnerable to freezing or evaporation, depending on temperature and pressure. A world with most of its water trapped as nightside ice could leave the dayside dry unless melting, and transport return water across the planet. Tidal locking does not decide which outcome occurs. It rearranges the conditions under which water must persist. The night side is not merely a cold half of the world. It could be a vast reservoir, a frozen archive of the planet's volatile history. If the atmosphere is thick enough, temperatures there might remain above collapse, and winds could prevent total freeze-out. If the atmosphere is thin, the night side could become a sink for carbon dioxide, water ice, or other gases, pulling them from the climate system. Once enough gas freezes out, the atmosphere weakens further, making the planet still colder and closer to collapse. This feedback could turn a marginal world barren without direct stellar destruction. Climate failure can occur quietly, through imbalance. The night side may therefore hold one of the hidden tests of Proxima b. It asks whether the planet can keep enough air moving and warm enough material circulating that darkness does not become a permanent drain. Tidal locking also affects magnetic protection in uncertain ways. A slowly rotating planet might have a weaker dynamo if rotation is essential for organizing fluid motion in the core, but the relationship is not simple. Internal heat, core composition, convection, and tidal effects all matter. A locked planet may still maintain a magnetic field under some conditions, while a freely rotating planet could still fail if its interior becomes too quiet. For Proxima b, this uncertainty links surface climate to the deep interior. The same gravitational relationship that may freeze the planet's sky into a fixed pattern could also influence internal heating, orbital evolution, and the strength of any magnetic shield. Habitability becomes three-dimensional. It is not only the light arriving from above, but also heat and motion rising from below, air moving around the globe, and particles striking from the star. The planet's locked face, if it exists, is only the visible sign of a deeper coupling between orbit, rotation, atmosphere, and interior. The idea of a permanent dayside and nightside can make Proxima b sound deeply alien, yet it also broadens the imagination of habitable worlds. Earth is not the only possible arrangement for a stable climate. A world may not need ordinary sunrises, seasons, or rotating weather belts to maintain liquid water somewhere on its surface. It may need only a durable way to move energy, preserve pressure, and protect its water inventory. Proxima b could have all of that, or none of it. The locked geometry does not answer the question, but it reveals what kind of answer is required. Any claim that the planet is Earth-like must pass through this fixed pattern of red light and darkness. Any claim that it is ruined must also confront the possibility that atmosphere, ocean, cloud, and rock can adapt to unfamiliar forcing. Under tidal locking, Proxima b would not be a second Earth in the ordinary sense. It would be a different experiment in planetary balance, one where habitability, if present, may gather not across a familiar turning globe, but in the carefully maintained exchange between a face that never leaves the star and a hemisphere that never sees it. Proxima b's present orbit is only the last visible line of a longer story. A planet does not simply appear where it is found. It grows inside a disk of gas, dust, ice, and rock around a young star, and the place where it gathers its first material can decide much of what it later becomes, around Proxima Centauri. That history is unusually important because the planet now moves very close to its star, in a region where warmth may be possible today, but where early conditions may have been severe. If Proxima b formed near its current orbit, then its ingredients, its water supply, its impacts, and its first atmosphere were assembled in a tight inner environment under a small star whose youth may have been energetic. If it formed farther out and migrated inward, then it may have carried a different inventory into the habitable zone, perhaps including more volatile material, perhaps also carrying scars from movement through the young system. The difference is not a technical detail. It may be the difference between a world that began nearly dry and one that arrived with enough water to endure loss. Planet formation begins in a disk that is both generous and selective. Close to a young star, temperatures are higher, and some volatile substances, including water ice, are harder to preserve as solid building blocks. Farther out, beyond regions where ice can remain stable, growing planets may incorporate more frozen material. Proxima B's case may be even more sensitive because its orbit lies close to a small star, where the amount of solid material available in the original disk may have been limited. A rocky planet can form close in if enough dust and pebbles gather efficiently. But there is a question of whether the disk around a low-mass star contained enough material at that distance to build a body of Proxima B's likely mass. If the local supply was too thin, migration becomes more plausible. The planet may have formed at a greater distance, where material was more abundant or more water-rich, and then moved inward through gravitational interaction with the disk or with other developing bodies. Migration is not an exotic exception in planet formation. Many planetary systems appear to have been rearranged after birth. Young planets interact with the gas disk that surrounds the star, raising waves in it and exchanging angular momentum, which can shift their orbits. Multiple planets can also tug one another into new paths. Some worlds may spiral inward, some may be pushed outward, and some may become trapped in resonances, where orbital periods settle into linked patterns. The final architecture of a system is not always a record of where each planet formed. It is often a record of motion, loss, collision, and survival. Around Proxima Centauri, the known inner planet Proxima d, and the possible wider companion Proxima c, if it exists, remind the system is not necessarily a single planet story. Even uncertain companions matter because a system with more than one planet can preserve clues about migration, spacing, and the stability of early orbits. Proxima b's formation path matters first for water. A planet born too close to a young red dwarf may begin with less water than a world formed beyond colder regions of the disk. It may still receive water later through impact by icy bodies, but delivery around a small star in a compact system is not guaranteed. If instead Proxima b formed farther out, it could have collected more ice before migrating inward. That sounds promising. But too much water creates another kind of uncertainty. A world with a deep global ocean may not resemble Earth, even if it is wet. Without exposed land, weathering cycles that regulate carbon dioxide on Earth may work differently or weakly. High-pressure ice could form at the base of deep oceans, separating water from rock and changing chemical exchange. A water-rich Proxima b might be habitable in some sense while still lacking the familiar geochemical balance that makes Earth stable. Migration can therefore supply what close formation may deny, but it can also transform the planet into something less Earth-like than the phrase second Earth suggests. Formation also shapes the atmosphere. A planet's first air can come from gases captured from the disk, gases released from molten rock, and volatiles delivered by impacts. If Proxima b formed close in, intense early radiation may have stripped light gases quickly, leaving behind a secondary atmosphere built later by volcanism and impacts. If it formed farther out and migrated inward while the disk still contained gas, it may have interacted with a different atmospheric environment. The timing matters. A planet that arrives close to the star while the star is still especially active may lose much of its atmosphere early. A planet that migrates after acquiring a large volatile inventory may retain some despite loss. A planet that arrives too late may have missed key delivery events. The present atmosphere, if it exists, would be a fossil of these timings, not simply a response to today's radiation. Impacts add another layer to the biography. Early planets grow through collisions, and those collisions can build, melt, strip, and enrich a world all at once. A giant impact can remove atmosphere, tilt a planet, alter rotation, and help form moons. Though stable moons around such a close orbit would be difficult to keep for long, smaller impacts can deliver water and carbon compounds. Or they can erode air depending on speed and angle. Around Proxima b, the impact history may have been influenced by migration. A migrating planet can disturb leftover planetesimals, sweeping up some, scattering others, and changing the pattern of bombardment. The planet's surface may preserve in its crust the record of whether impacts acted more as suppliers or as destroyers, but that record remains beyond reach. Rotation is part of the same hidden history. If Proxima b formed in place, its close orbit may have allowed tidal forces to slow its spin early. If it migrated inward, it may have begun with a different rotation state and only later been drawn toward locking. The timing of this slowing could influence climate, magnetic field development, and atmospheric circulation. Later tidal locking could freeze a climate pattern after much of the volatile history had already occurred. If the orbit retained a slight eccentricity, tidal flexing could generate internal heat, perhaps supporting volcanism, but too much heating could also stress the interior and climate. Again, the issue is balance. The same process that might keep a planet geologically alive could also make it more restless and less stable. Migration raises one more question. Why did the planet stop where it did? A body moving inward through a disk does not automatically halt in the habitable zone. It may fall closer, become trapped at the inner edge of the disk, settle into resonance with another planet, or stop when the gas disperses. Proxima b's current orbit could therefore be a product of timing rather than destiny. The planet may occupy a life-friendly distance not because it was built for that region, but because the disk vanished. Resonances shifted, or gravitational interactions ended while it happened to be there. This possibility gives the habitable zone a more fragile meaning. It may not be a cradle. It may be a parking place after a long rearrangement. Such a history would not make habitability impossible, but it would remove any sense that the system was naturally arranged for comfort. This uncertainty affects every comparison with Earth. Proxima b formed around a low-mass flare star in a compact region, where familiar labels may hide very different processes. Even if the planet has a similar mass, receives comparable total energy, and holds rock and water, its origin may have followed a path that Earth never did. It could be a migrated ocean world, a stripped-inner planet, a dry survivor, or a volatile rich body remade by radiation. Each possibility carries a different surface, different atmosphere, and different meaning for the word Earth-like. The birthplace changes everything because it changes what the planet had before the star began taking things away. For now, the formation story remains mostly inferential. The orbit is known, the mass is partly constrained, and the star's nature can be studied, but the planet's composition is still hidden. No direct sample of its atmosphere, surface, or interior can yet decide whether migration happened or whether local formation was enough. Models can show plausible paths, but several paths remain open because the key evidence is missing. That absence defines the next stage of the mystery. Proxima b is not only a planet in a present-day habitable zone, it is the outcome of an unseen childhood, and the difference between near a second Earth and complete disaster may have been written before the planet ever settled into the orbit that made it famous. Possible surface worlds begin where the measurements stop. Proxima b has a mass that places it in the territory of rocky planets, an orbit that places it near the thermal threshold for liquid water, and a star that places every gentle assumption under stress. Beyond that, the planet becomes a set of competing landscapes, each plausible enough to consider and uncertain enough to resist belief. It may be a dry sphere of dark volcanic rock, its early water stripped away by radiation before the surface could settle into climate. It may be an ocean world, carrying water from a colder birthplace into the red light of Proxima Centauri. It may be partly frozen, with ice gathered on the night side and a milder region near the boundary between day and night. It may even hide water below a crust of ice, making its most important environment invisible from space. None of these versions is fantasy. Each grows from known planetary processes. The difficulty is that Proxima b has not yet offered the evidence that would choose among them. A dry Proxima b is the simplest disaster to imagine, but it would not necessarily be dramatic in appearance. It might look quiet and airless, or nearly airless, with a surface exposed to radiation and micrometeorite impacts. If the planet formed close to its star and endured a long active youth, water could have been lost early through atmospheric escape. Ultraviolet light could split water vapor. Hydrogen could leak into space, and oxygen could react with the surface. Over time, oceans that once existed might shrink, vanish, or remain only as minerals altered by water in the past. Such a planet would still be important. It would show that the habitable zone around a red dwarf can contain worlds that have already spent their habitability before they are observed. In this version, the orbit is not a promise but a remnant, a place where water could exist now only if earlier history had allowed it to remain. The dry world scenario also raises questions about geology. A planet more massive than Earth might hold internal heat for a long time, but that does not guarantee active resurfacing or volcanic replenishment. If volcanism persists, gases could still be released from the interior, perhaps building a secondary atmosphere after early loss. If the interior has become too quiet, the surface may stay exposed, with little ability to repair what the star removes. Dryness is not simply the absence of oceans. It is the breakdown of cycles that connect interior, surface, and air. Without water, weathering changes. Without weathering, climate regulation weakens. Without a stable atmosphere, even a planet in the right orbit can become rock-lit by a star that gave it too much. The ocean world version is more hopeful at first, but it carries its own complications. If Proxima b formed farther from the star and migrated inward, it may have collected abundant ice before reaching its current orbit. Under enough pressure and warmth, that ice could become a deep ocean. A global ocean would provide radiation shielding, thermal storage, and a stable medium for chemistry. It could help move heat from the day side toward cooler regions, reducing extremes caused by tidal locking, beneath a red sky, with clouds gathering over the warm hemisphere. Such a planet might seem like the nearest expression of habitability, yet a water-rich Proxima b would not necessarily be Earth-like. If the ocean is too deep, high-pressure ice may form at its base, separating liquid water from the rocky mantle. That separation could limit the exchange of minerals and chemicals needed for long-term geochemical cycles. A world with water everywhere may lack the exposed continents that help Earth regulate carbon dioxide over geological time. Too much water can become a different form of isolation. A planet can be wet and still chemically constrained. Between dry rock and global ocean lies a more uneven possibility. Proxima b may have retained some water, but not enough to cover the planet completely. On a tidally locked world, water could migrate according to temperature. The day side might lose exposed water through evaporation, while the night side could trap ice in permanent darkness. The Terminator region could become the most stable environment, where starlight is weak but persistent, and temperatures may allow liquid water if the atmosphere is dense enough. This version produces a planet of strong contrasts rather than a single simple climate. There may be dry illuminated basins, ice fields in darkness, and regions of melt or cloud near the boundary. The result could be habitable only in patches, and those patches might shift with atmospheric pressure, ocean circulation, and volatile exchange. A planet like this would challenge the habit of asking whether a whole world is habitable. The better question may be whether any region remains stable enough, wet enough, and protected enough for chemistry to persist. An ice-covered Proxima b is another possibility, especially if the planet keeps water but receives too little effective surface warmth, or if clouds, circulation, and atmospheric composition push it toward freezing. Ice is often treated as a sign of failure, but it can also preserve and protect. On moons such as Europa and Enceladus in the outer solar system, ice crusts cover internal oceans maintained by heat from below. Proxima b is very different from those moons, but the general lesson is that surface ice does not automatically erase subsurface water if the planet has internal heat, tidal flexing, or residual energy from formation. A layer of liquid water could survive beneath ice even when the surface is harsh. Such a world would be difficult to classify. From a distance, it might look uninviting, perhaps bright in places, cold in others, and quiet under Proxima's red light. Beneath the crust, however, water could remain shielded from radiation, in contact with rock if the ocean is not sealed away by high-pressure ice. That contact would matter because water interacting with rock can create chemical gradients, the differences in energy that life can exploit. This hidden ocean version is both promising and sobering. It allows habitability to survive beneath hostile conditions, but it moves the strongest possibility away from direct observation. A surface biosphere might be absent, while subsurface chemistry remains possible. Detecting such an environment across interstellar distance would be hard. The planet might not show obvious atmospheric signs of life, especially if the ocean is sealed. Even if living chemistry existed below, it might leave only weak traces at the surface, carried by fractures, volcanism, cryovolcanism, or none of these at all. The nearest potentially habitable planet could therefore be habitable in a way that remains almost completely hidden. There is also the possibility of a Venus-like or superheated Proxima b, not because it is outside the habitable zone, but because atmosphere can transform received energy into a trap. If the planet developed a dense greenhouse atmosphere, surface temperatures could rise beyond the range where liquid water remains stable. Water vapor itself could strengthen warming, and a runaway process could leave behind a dry, hot surface with a thick atmosphere shaped by loss. Around Proxima Centauri, the spectrum of light and the history of stellar activity would influence this path in ways that differ from the inner solar system. A hot Proxima b would be a warning against equating low stellar brightness with safety. The planet may orbit a faint star and still be too warm if its atmosphere pushes the climate in that direction. The same missing air that could make it too cold or exposed could, in another form, make it too hot. Each surface world depends on linked unknowns. How much water did Proxima b begin with? How much did it lose? Does it have an atmosphere? And what is that atmosphere made of? Does it rotate in a locked state? Does it have continents, oceans, ice caps, volcanism, a magnetic field, or plate tectonics? These questions combine into whole planetary identities. A thick atmosphere changes tidal locking, an ocean changes heat transport, volcanism changes atmospheric survival, ice changes radiation exposure, migration changes water supply, stellar flares change chemistry. Proxima b is not one mystery but a knot of interdependent processes, all compressed into the nearest possible extrasolar world. That is why the most honest image of its surface is not a picture, but a branching set of outcomes. One branch leads to dry rock, another to a deep ocean, another to ice and hidden water, another to a patchwork twilight climate, another to a greenhouse world. Some branches preserve the hope that Proxima b could be meaningfully habitable. Others turn it into a cautionary example of how little the habitable zone can guarantee. The planet has not yet chosen among these in the evidence available from Earth. It remains unseen, and in that invisibility its possible surfaces gather quietly, each waiting for the observation that would make the others fade. Proxima Centauri is not a simple planetary system just because its most famous world is Proxima b. Once a star has revealed one planet, every small irregularity in its motion begins to matter more. The observer no longer sees a lone wobble against a quiet background, but a layered signal where several causes may be hiding at once. Around Proxima, that task is made harder by the star itself. Magnetic activity can shift spectral lines. Spots can rotate across the visible surface. Flares can disturb the light. Instruments can carry their own tiny patterns. A planet can pull on the star with a rhythm that looks clean only after many sources of false motion have been removed. This is why the other proposed worlds in the system are more than side notes. Proxima d and the disputed Proxima c show how delicate the boundary can be between detection and interpretation, between a real planet and a pattern that only resembles one. Proxima d is the inner and smaller case. Its signal was noticed as an extremely weak rhythm in radial velocity data, a periodic tug repeating every little more than 5 Earth days. The planet inferred from that motion is far lighter than Earth, orbiting much closer to Proxima Centauri than Proxima b does. It lies inside the habitable zone, too near the star for ordinary surface habitability under simple assumptions, and it is almost certainly exposed to the same active stellar environment at even closer range. If Proxima b is a planet where hope and danger remain in conflict, Proxima d is more clearly an example of proximity without comfort. Its value lies less in the possibility of life, and more in the act of finding it at all. A body with only a fraction of Earth's mass creates an extraordinarily small stellar wobble. Detecting that pull around an active red dwarf requires instruments and analysis precise enough to work near the edge of what the method can do. Proxima d therefore changes the system in a subtle way. It shows that the nearest star may host not only a potentially temperate planet, but a compact architecture of small worlds whose signals are barely strong enough to separate from noise. If such a small world can be detected around Proxima, then other low-mass planets around nearby red dwarfs may be waiting beneath the limits of older surveys. The galaxy may contain many compact systems where terrestrial planets do not announce themselves with dramatic signatures, but with slight repeated motions that become visible only after patient measurement. Proxima d is inhospitable by most expectations, yet it widens the search by proving how faint a planetary signal can be and still leave a measurable trace. The inner planet also affects the interpretation of Proxima b's history. Multiple planets can point to migration, disk structure, and the way material was distributed around the young star. A compact inner system may suggest that planets formed or moved through crowded regions where gravitational interactions mattered, even if Proxima d has little direct bearing on habitability. Its presence means Proxima b should not be treated as an isolated object. It belongs to a system, and systems preserve histories. The spacing between planets, the stability of their orbits, and the possible absence or presence of companions all help reconstruct the architecture that shaped Proxima b's water, atmosphere, and final orbit. The difficulty is that each additional planet must first survive the test of confirmation, and around Proxima Centauri that test can be severe. Proxima c occupies a different kind of uncertainty. It was proposed as a much wider companion, a candidate planet with a long orbital period and a signal much harder to establish. If real, It would orbit far beyond Proxima b in a cold outer region, possibly with a mass higher than Earth's and a very different formation story. Such a planet would matter because it could provide evidence for a broader system architecture, perhaps one in which inner and outer worlds formed in distinct zones. It might also influence the early delivery of icy bodies or the dynamical environment in which Proxima b evolved. A distant companion can act like a quiet sculptor, not by warming a planet or shaping its daily climate, but by helping determine what material moved inward, what was scattered away, and how stable the inner orbits remained. But Proxima c has never had the same standing as Proxima b. Its evidence has been contested, and that contest is part of the lesson. A long-period radial velocity signal is vulnerable to confusion with slow instrumental effects, stellar cycles, and subtle errors in data extraction. When the expected wobble is low in amplitude and spread across years, the distinction between planet and artifact becomes harder. A star like Proxima Centauri does not provide a blank slate. It brings its own rhythms, and any apparent planetary period must be separated from them with great care. Some studies have supported the possibility of Proxima c, while later analyses have challenged the interpretation, suggesting that the original signal may have arisen from systematic effects rather than a true companion. This does not make the initial work careless. It shows how planetary discovery often advances through stress testing. A signal appears. It is modelled. It is compared against stellar activity. It is checked by different instruments and methods. Then other researchers ask whether the same data can be explained another way. A planet becomes secure only when the planetary explanation remains the best one after these alternatives have been pressed against it. Proxima c remains suspended because that process has not closed in one direction. The candidate is interesting enough to remember, but uncertain enough to treat with caution. The contrast between Proxima d and Proxima c is instructive. The inner world produces a short, repeating signal that can be sampled across many orbits in a compact observing campaign. The disputed outer candidate would take many years to trace, giving fewer cycles and more opportunity for slow noise to masquerade as orbital motion. One signal is tiny because the planet is light. The other is difficult because the possible orbit is long, and the evidence must remain coherent across extended time. Both cases show that exoplanet detection is not simply a matter of stronger telescopes seeing farther. It is often a matter of extracting patterns from instability. The instrument must be stable. The star must be understood. The mathematics must not turn coincidence into certainty. Around Proxima, even the nearest system can remain elusive because nearness does not remove complexity. The crowded and uncertain nature of the system changes the emotional tone of Proxima b. It is tempting to make the story rest entirely on one planet, one possible second Earth, one nearby answer to an ancient question. But Proxima d and Proxima c, one confirmed through a delicate small signal and the other left in dispute, remind the system is a web of measurements rather than a single revelation. Each planet, candidate, and absence shapes the field around Proxima b. The presence of a small inner world may support a picture of compact planet formation. The uncertainty of a wider world complicates the story of outer reservoirs and migration. Future detections could change the balance again, revealing more planets, ruling out candidates, or finding that the system is simpler than some signals once suggested. This uncertainty is not a failure of knowledge. It is how knowledge behaves near its frontier. The more precise the measurements become, the more they reveal both planets and the weaknesses in the methods used to find them. Proxima Centauri, because it is so close, becomes a proving ground not only for planetary habitability, but for the discipline of detection itself. A signal measured in the motion of a star must pass through stellar noise, instrument noise, statistical judgment, and independent confirmation before it can become a world with a secure name. Proxima b has crossed that threshold strongly enough to stand at the centre of the system's habitability question. Proxima d has emerged as a remarkable small inner planet and a demonstration of modern precision. Proxima c remains more ghost-like, a possible outer body whose reality depends on evidence still being weighed. Together they make the nearest planetary system feel less like a finished map than a page still being developed in faint ink. The star has already yielded more than one hint of architecture, but not yet enough to make the architecture settled. What matters is that Proxima b does not orbit in a narrative vacuum. Its chances of being a second Earth or a complete disaster may depend partly on a history written by companions, disk migration, impacts, and missing worlds searched for at the edge of measurement. The nearest star system is crowded not only with planets and candidates, but with ambiguity, and that ambiguity becomes the next obstacle before the planet itself can be seen. Seeing Proxima b will require a different kind of patience from finding it. The planet was discovered through the motion it gives its star, a gravitational trace repeated in spectral lines. But the next stage asks for light from the planet itself. That light is faint beyond ordinary intuition. Proxima b is close to its star, and from Earth the two appear separated by a tiny angle on the sky, so small that the planet sits almost inside the glare of the red dwarf that illuminates it. The problem is not only distance, it is contrast. A star is a furnace of plasma. A rocky planet is a dim reflector and radiator, sending back only a thin fraction of the energy it receives or glowing weakly in infrared heat. To detect Proxima b directly, an instrument must suppress or separate the star's light well enough that the planet's far weaker signal can be measured. The nearest potentially habitable world is therefore hidden not by being far in the usual astronomical sense, but by being drowned in the light of the star it orbits. Direct imaging sounds simple because it resembles ordinary seeing, but for exoplanets it is closer to controlled subtraction. A telescope must gather light with extreme precision, correct for blurring in Earth's atmosphere if it is on the ground. Remove scattered starlight and search for a small point at the expected orbital distance. Coronagraphs can block the central glare inside a telescope, while starshades, if ever used in space for such targets, would fly far from the telescope and cast a shadow to suppress the star before its light entered the optics. Interferometry offers another route, combining light from separated telescopes so that the star can be partly cancelled while nearby planetary light remains detectable. Each approach carries difficulty. The alignment must be exquisite. The instrument must be stable. The star's own variability must be understood. A flare, a spot, or a magnetic feature on Proxima Centauri can change the light being removed, and a flawed subtraction can create patterns that look more meaningful than they are. The act of seeing the planet is also the act of proving that what remains after the star is suppressed truly belongs to the planet. The closeness of Proxima Centauri gives this effort a narrow advantage. Because the system is nearby, the planet's apparent separation from the star is larger than it would be for an identical world at greater distance. That is one reason Proxima b remains such an important target. Yet the advantage is limited by the planet's tight orbit. It is close to Proxima Centauri in physical distance, so even the nearest star system does not spread it widely across the sky. The planet may move through phases like the Moon or Venus, showing different portions of its illuminated hemisphere depending on orbital geometry. If it does not transit the star as seen from Earth, then a major pathway for atmospheric study is mostly unavailable. Transit spectroscopy depends on starlight filtering through the edge of a planet's atmosphere during a crossing, revealing gases that absorb certain wavelengths. Proxima b does not appear to offer that repeated alignment, so the atmosphere must be approached by harder methods, likely by separating the planet's own reflected or emitted light from the stellar glare. If that light can be isolated, it may carry the information that the radial velocity signal could never provide. Different molecules absorb light at different wavelengths. Water vapor, carbon dioxide, methane, oxygen, ozone, and other gases can leave spectral fingerprints, though each one has to be interpreted with caution. A hint of water vapor could point toward a wet atmosphere, but it could also depend on altitude, temperature, and ongoing escape. Carbon dioxide might suggest greenhouse warming, volcanic outgassing, or a dense atmosphere. But its meaning would change with pressure and climate. Oxygen could be exciting, yet it might also arise from water loss without life. Methane could be biological, geological, or photochemical depending on context. No molecule would speak alone. A real atmospheric reading would be a pattern, and the pattern would have to be compared against the star's radiation, the planet's mass, the possible surface temperature, and the history of atmospheric escape. The first spectrum of Proxima b, if it comes, may not announce habitability. It may narrow the range of possible worlds. Even a simple detection of atmosphere would be transformative. If Proxima b has no substantial air, many of its gentler scenarios would weaken at once. A bare rock could still have subsurface secrets, but the image of surface water under a moderated climate would be difficult to defend. If a thick atmosphere is present, the question would move to composition and climate. A carbon dioxide-dominated envelope could keep the planet warm, or in excess could point toward a harsher greenhouse state. A nitrogen-rich background might make climate more Earth-like. Though nitrogen itself is difficult to identify remotely, clouds could conceal the lower atmosphere and surface, complicating the spectrum but also revealing circulation. Seasonal changes would not be expected in a familiar way if the planet is tidally locked, yet phase changes as it orbits could show how heat and clouds are distributed between the day side and night side. Observations over time could therefore turn a point of light into a crude climate map, not with continents and coastlines, but with brightness, temperature, and atmospheric behavior. The surface will be harder still. A dry world, an ocean world, an ice-covered world, and a cloudy greenhouse world may reflect and emit light in different ways, but the differences can be subtle from interstellar distance. Oceans can produce a glint when starlight reflects at certain angles, though detecting such a signal around Proxima b would be extremely difficult. Ice may appear bright, but under red dwarf light its behavior differs from the ice familiar under the sun, and clouds can mimic or hide bright surfaces. Vegetation like Earth's would be an extraordinary claim and is not something that can be assumed. Even if life existed, it might use different pigments under red light, or leave no strong surface signature at all. A barren mineral surface could also vary in colour and reflectance depending on rock type and weathering. The first images, if they are ever achieved, may not look like images in the ordinary sense. They may be measurements of brightness at different wavelengths, changing across the orbit, gradually assembled into a statistical portrait of an unseen surface. Proxima's activity will remain a constant obstacle. Flares can brighten the star and alter the radiation hitting the planet, but they can also provide occasional opportunities. A flare passing through or reflecting from a planetary atmosphere might reveal how that atmosphere responds to sudden energy, though the signal would be difficult to isolate. More often, stellar activity is a source of contamination. Star spots can change the apparent spectrum of the star. Bright regions can rotate in and out of view. The star's surface is not uniform, and if its changing light is not modelled carefully, the leftover signal could be mistaken for planetary absorption or emission. Around a quiet star, the difficulty of direct imaging would already be immense. Around Proxima Centauri, the star is both the thing that reveals the planet by its tug and the thing that hides the planet by its restlessness. The future of observation may therefore depend on a combination of instruments, rather than a single dramatic breakthrough. Large ground-based telescopes may attempt high-resolution imaging and spectroscopy with adaptive optics, using deformable mirrors to correct atmospheric distortion. Space telescopes could avoid Earth's atmosphere and offer greater stability, especially if designed for high-contrast imaging. Long baseline interferometers could eventually search for thermal emission from nearby rocky planets, measuring their heat and perhaps testing whether night sides are frozen or warmed by circulation. Repeated radial velocity measurements will continue to refine mass and orbital behavior. Astrometry, the precise tracking of a star's position on the sky, could help constrain inclinations and possible additional companions. Each method sees a different shadow of the planet. Together, they may assemble the first reliable environmental picture. That picture may arrive slowly. It may begin with a better mass, then a limit on atmosphere, then a weak spectrum, then a possible climate interpretation. The most important discoveries may be negative: no atmosphere, no strong water signal, no evidence for heat redistribution. Or they may be partial and ambiguous: a possible atmosphere, but uncertain pressure, a hint of carbon dioxide, but no clear water, thermal behavior consistent with air, but not enough to prove habitability. This is how the nearest world may come into focus, not as a sudden blue sphere, but as a sequence of constraints tightening around the truth. Proxima b has already been found in the motion of its star. To understand it, astronomy must now learn to hear the planet's own light beneath that star's glare. What waits there may be a wounded rock, a hidden ocean, a clouded climate, or a world with enough protection to keep the question of habitability alive. The next step is not merely seeing the neighbour, it is separating a planet from the light that both sustains it and conceals it. Proxima b is close enough to tempt engineering and far enough to expose the cruelty of interstellar distance. The planet circles the nearest known star to the Sun, and yet the gap between the solar system and Proxima Centauri remains so wide that ordinary spacecraft fade into almost geological timescales. The Voyager probes, among the most symbolic travellers humanity has ever released, are moving through interstellar space, but they were never built to reach another star. Their paths are departures, not arrivals. A conventional probe aimed toward Proxima would require many thousands of years, long enough for civilizations, languages, and scientific priorities to change beyond recognition before the first close observations could return. This is why the thought of visiting Proxima b does not begin with a larger version of familiar rockets. It begins with abandoning much of what a spacecraft has traditionally been. To reach the nearest possible planetary target within anything like a human timescale, the machine must become extremely small, extremely fast, and driven by energy that does not have to be carried on board as heavy fuel. The most famous version of this idea is Breakthrough Starshot, a proposed attempt to send gram-scale probes toward the Alpha Centauri system using powerful Earth-based lasers and ultralight sails. A tiny spacecraft, sometimes imagined as a chip with instruments, communications, guidance, and power systems, would be attached to a reflective sail. A vast laser array on Earth would focus light onto that sail, pushing it with radiation pressure until it reached a significant fraction of the speed of light. After the acceleration phase, the probe would coast across the space between stars, unable to brake in any ordinary way, eventually passing through the Alpha Centauri neighborhood at tremendous speed. Such a mission would not arrive like an orbiter settling into careful study. It would be a flyby, a brief crossing of a distant system after decades of silence and travel. A probe moving at a fifth of light speed could cross the distance to Proxima Centauri in a little over 20 years, with its data taking a little more than 4 additional years to return to Earth. Those times are still long by the rhythm of individual projects, but they belong to human memory rather than deep history. A child alive at launch could still be alive when the first signal came back. That possibility gives Proxima b a special place in the imagination of future exploration. It is not merely the nearest interesting exoplanet. It is the nearest world for which an interstellar reconnaissance mission can be described without surrendering completely to thousands of years. The same closeness that makes Proxima b scientifically urgent also makes it the first plausible target for a new kind of spacecraft. Yet the concept is surrounded by difficulties that are not incidental. They are the mission. The laser array would have to deliver enormous power with extraordinary precision, holding its beam on a tiny sail as it accelerates violently away from Earth. The sail would have to survive intense illumination without tearing, melting, spinning out of control, or deforming in ways that waste the push. The probe would have to endure acceleration far beyond anything used in ordinary spaceflight, then survive decades in a cold, dusty, radiation-filled environment. Even tiny grains of interstellar dust become dangerous when encountered at a fraction of light speed. A collision with a particle too small to notice at ordinary velocities could damage a sail, instrument, or communication system. The probe would need to be both nearly weightless and unexpectedly resilient, a combination engineering rarely grants easily. Communication may be the hardest quiet problem. A gram-scale probe passing Proxima at high speed would have very little power and a very small transmitter, yet it would need to send data across more than 4 light-years back to Earth. The signal would spread and weaken across the distance, arriving as an extremely faint trace that would require large receiving arrays and careful timing. The probe would also have to know where to point its transmitter while moving rapidly through the system. It would need to image or measure targets during a flyby lasting hours or days, store or transmit useful information, and aim that information home. A mission could send many probes to increase the odds that some survive and some pass close enough to useful targets, but each one would still face navigation and communication limits. At interstellar speed, a small targeting error becomes a vast miss. Proxima b is near in stellar terms, but its planet-scale encounter zone is tiny compared with the journey. The flyby itself would be strange. There would be no long orbital campaign, no repeated passes, no careful descent through atmosphere, no lander watching a horizon. The probe might flash through the system fast enough that every observation has to be planned before arrival and executed automatically. It could search for the planet's brightness, attempt crude images, measure reflected light, look for signs of an atmosphere, or gather data on dust and magnetic fields in the outer system. If aimed well and functioning properly, it might provide the first direct close-range glimpse of a planet around another star. The images would probably not resemble the romantic expectation of a blue globe filling the frame. They might be low resolution, partial, noisy, and compressed by the realities of distance and speed. But even a few pixels from Proxima b would carry a meaning unmatched by any model. A pixel could be bright or dark, variable or steady, suggestive of clouds, ice, ocean, or bare rock. A spectrum could hint at air or its absence. A thermal measurement could test whether heat moves from the day side to the night side. The first interstellar glimpse may therefore be modest in appearance and enormous in consequence. It could narrow the possible worlds. A dry, airless Proxima b would teach one lesson. A cloudy world with an atmosphere would teach another. An icy planet, a greenhouse planet, or a world with signs of heat redistribution would each reshape the argument around red dwarf habitability. Even a failure to find comforting evidence would not be wasted. If the nearest habitable zone planet around the nearest red dwarf is stripped and severe, That result would matter for the many small planets found around similar stars. It would suggest that warmth alone is not enough, and that stellar activity may close doors that orbital distance appears to open. If Proxima b instead retains an atmosphere and perhaps water, the result would be equally profound, because it would show that planets can survive close to active red dwarfs under at least some conditions. The mission would not only be exploring one planet, it would be testing a whole category of possible homes in the galaxy. That is why Proxima b remains balanced between invitation and warning. The planet's nearness makes it feel almost chosen, but nothing in the evidence says it was made gentle. It may be an ocean-bearing survivor, a twilight climate under red light, a dry remnant of early loss, a frozen world with hidden water, or a planet whose atmosphere turns promise into heat. Each uncertainty would meet the flyby at the same point the need for direct evidence. A future probe would not carry human longing in any literal sense. It would carry instruments, fragile systems, and the accumulated patience of generations of astronomy. Yet its passage would represent a threshold in how the nearest stars are known. For all of history, Proxima Centauri has been light, motion, inference, and measurement from afar. A successful flyby would turn the nearest exoplanet system into a place crossed by human technology, even if only for a moment and only by machines far smaller than the dreams attached to them. The deeper meaning of such a mission is not conquest and not escape. Proxima b is not a backup Earth waiting to be claimed, and the current evidence gives no permission for that fantasy. It is test world, close enough to force attention and difficult enough to humble expectation. It asks whether the galaxy's most common stars can shelter stable environments, whether an Earth-sized planet in a habitable zone can survive a red dwarf's long unrest, and whether the first reachable exoplanet will reward hope or correct it. The answer may be mixed. As planetary answers often are, Proxima b could be partly ruined and partly preserved, hostile on the surface and interesting below, not a second Earth and not complete disaster, but something more instructive than either phrase. Until it is seen, the nearest world beyond the sun remains defined by that tension. It is close in light years, distant in practice, promising in orbit, dangerous in context, and waiting at the edge of the first true interstellar question, whether the closest possible Earth-like planet is a refuge, a warning, or the beginning of a much more complicated map. In the end, Proxima b remains quiet because the most important evidence has not yet crossed the distance. The star is known, the orbit is known, and the danger is real enough to restrain every easy hope. Yet the planet itself is still hidden behind glare, inference, and the limits of instruments waiting to improve. That hiddenness gives the world its strange power. It is not a confirmed second Earth, and it is not yet a confirmed ruin. It is a nearby test of what habitability means when the star is small, active, and long-lived, when warmth comes with radiation, when an orbit can invite water while history may have taken it away. Around Proxima Centauri, the familiar idea of Earth-likeness becomes narrower and more careful. It must pass through atmosphere, tidal locking, formation, water loss, climate circulation, and the silent endurance of rock and air under red light. Perhaps the planet has kept enough protection for stable places to exist. Perhaps any water lies sealed under ice or held in darkness. Perhaps the surface is dry, altered, and exposed, preserving only the memory of a chance that passed early. Each possibility is still part of the same unfinished map. What matters is that the nearest world has already done something important. It has made the question specific. Somewhere beyond the sun, at the closest stellar shore, a planet moves through a short orbit around a faint red star, carrying either a warning, a promise, or a more complicated answer that does not fit either word. For now, it remains unseen, patient in its distance, waiting for light from future instruments, or some first small messenger crossing the dark between stars. And until that evidence arrives, Proxima b stays balanced at the edge of knowledge, close enough to matter, distant enough to keep it